Let's take a look at another example. Is the following set of vectors a basis for R3? Okay, so again, we want to determine if the vectors are linearly independent and if they span all of R3. So to do that, what we can do is we can take our vectors, and we know that there's one matrix that we could look at that will tell us all we need to know. So I'm going to start by placing the column vectors, the vectors in my set as the columns of the matrix. Okay? And I want to see if I could express a few vectors as a linear combination of these vectors and how many solutions I have. So the first one, in order to determine if the vectors are linearly independent, I want to know how many solutions I get if I take a linear combination of these vectors and set it equal to 0, 0, 0. Okay? Set it equal to the 0 vector. We don't usually write in the 0 vector. You can if you want, but I'm going to leave it off. But looking at that will help me determine if the vectors are linearly independent. To determine if the vectors span R3, I want to see if the linear combinations of these vectors can be used to express all the vectors in the standard basis of R3. So that means, in this case, I, j, and k. So vector I is 1, 0, 0. Vector j is 0, 1, 0. Vector k is 0, 0, 1. Okay? And if each of the vectors I, j, and k can be expressed as a linear combination of these vectors, since I, j, and k span R3, these vectors must also span R3. Okay? So in order to get the information we need this matrix in reduced row echelon form. We really don't want to do that by hand. So let's plug it into our calculator here. Negative 5, 3, 1, 0, 0. That's row 1. Negative 1, 4, 2. 0, 1, 0, that's row 2, and negative 2, 2, 0, 0, 0, 1, that's row 3. Tell the computer to get into reduced row echelon form and print it so it's nice and pretty and easy to look at. Okay, so the reduced row echelon form of our matrix is 1, 0, 0, negative 2 over 25, 3 over 25, negative 11 over 25. Row 2, 0, 1, 0, negative 2 over 25, 3 over 25, 3 over 50. And row 3, 0, 0, 1, 3 over 25, 8 over 25, negative 17 over 50. Okay, so now I can use this matrix to tell me if the vectors are linearly independent and if the vectors span R3. Okay, so let's start with linear independence. With linear independence, remember that's when the augmented part is 0, 0, 0. Okay, and after doing all the row operations, the augmented part would still be 0, 0, 0. And we could see here that our three variables would each have exactly one solution, right? X equals 0, Y equals 0, Z equals 0. Okay. In other words, if I look at just the coefficient matrix here, I don't have any free variables. That's really what I'm looking for. Do I have any free variables? No, I don't. The rank of the matrix is 3. I have 3 columns in my coefficient matrix. Since 3 minus 3 is 0, I have no free variables. So yes, the vectors are linearly independent. Okay. Now, do they span R3? So remember, this is kind of really 3 linear systems of equations. with the same coefficient matrix in each system. So for the first system, I'm looking to see if I can express vector I as a linear combination of these vectors. So I'm going to first be looking at this matrix here. Okay? And I can see that I do have a solution, right? I can express, I don't have a row that looks like 0, 0, 0, and then on the other side of the augmented part, something that's not 0. That would tell me no solution. I don't have that. So I is in the span. Vector I is in the span of these three vectors. Okay, now look at the next column for vector j. For vector j, I look at the coefficient matrix and I look at the second column in the augmented part. And again, I don't have any lines that will tell me no solution, any rows that suggest no solution. So vector j can be expressed as a linear combination of my original set of vectors. And same thing for vector k. For vector k, it's the last vector in my augmented part, so I look at my coefficient matrix, I look at the last column here, and I don't have any rows that say no solution, which means I do have a solution, which means I can express vector k as a linear combination of these vectors. Because I can express I and j and k as a linear combination of these vectors, that means that these vectors will span all of R3. Since the vectors are linearly independent and they span R3, that means the vectors form a basis of R3. Okay? So I could use these three vectors, a linear combination of these three vectors. Any vector in R3 can be expressed as a linear combination of these three vectors. And that linear combination would be unique. There's only one way to choose the coefficients of these vectors to express any vector in R3 as a linear combination of these three vectors.